Welcome to Algorush. You and we interact with databases literally all day long. But have you ever really stopped and thought about what's going on under the hood? When you hit save or post a comment, how does a database physically put that information onto a disk so it can find it again in a split second out of maybe billions of other records? Well, today, we're going to pull back the curtain and find out.
So you might be thinking, this sounds simple enough, right? Why not just dump everything into a giant text file? I mean, we could just keep adding new data to the very end. But that super simple idea just completely falls apart the second you need to do anything, well, efficiently. Just imagine trying to find one specific user out of millions, or updating a single piece of their information without having to rewrite the entire file. It would be an absolute nightmare.
And the real heart of the problem, the reason we can't do that is this: the massive, and I mean massive, speed gap between memory and disk. Getting data from RAM, we're talking nanoseconds, blazing fast. But getting it from a physical disk, we're talking milliseconds. That might not sound like much, but it's a difference of several orders of magnitude. It's like comparing the time it takes you to blink to the time it takes to get a pizza delivered. This giant gap is the one fundamental challenge that every database storage system has to overcome.
So to conquer that performance canyon, simple files are out. We need specialized ways to organize our data, and these systems are all trying to hit three main goals. First, storage efficiency. We don't want to waste a bunch of space. Second, access efficiency. We've got to find any piece of data as fast as humanly possible. And third, update efficiency. When we change something, it should cause the absolute minimum amount of work on the disk itself.
So what's the piece of magic that does all this? Well, it's called the storage engine. Honestly, it's the unsung hero of every database. It's this incredibly sophisticated piece of software that works tirelessly in the background, arranging all your data on disk so it can be stored and found with mind-blowing performance.
The storage engine is so absolutely critical that many of the big databases you've heard of, like MySQL or MongoDB, are actually designed with plug-and-pluggable engines. This is so cool. It means you can literally swap out the entire storage layer to perfectly tune the database for your specific needs. Are you building an app with tons of reads, or are you trying to handle a fire hose of incoming data? The engine you pick is going to make or break your performance. Okay, so how do these engines actually pull this off? Well, over decades of innovation, two main strategies, two different schools of thought, have really come to dominate the field. And understanding the difference between these two is the key to unlocking how pretty much every modern database really works. All right, let's kick things off with the tried and true classic, the foundation for most of the relational databases out there, the B tree. If you need a metaphor, think of it as the ultimate meticulous obsessive-compulsive organizer.
So what is a B tree? At its core, it's a kind of self-balancing tree structure. Its whole job is to keep your data perfectly sorted on disk, all the time. Because everything is so neatly organized, the database can navigate from the top of the tree, the root, all the way down to the leaf that holds your specific piece of data incredibly fast. It's just like using the index in the back of a textbook to find exactly the page you need.
Now, the key mechanic, the thing that really defines a B tree, is the concept of an in-place update. This is pretty straightforward. When you need to change a record, the database finds its exact location in the file structure and just overwrites the data right there in that spot. Nothing else moves, it's a direct, targeted update.
And this in-place update model is what makes B trees absolutely fantastic for read-heavy workloads. Since everything has a precise, sorted home, finding a single record or scanning a range of them, like show me all my orders from last month, is incredibly fast. This is exactly why B trees are the heart of most online transaction processing, or OLTP systems. These are the databases that power the websites and apps we use every single day.
Okay, so that's one way. Now let's flip the script and look at a completely different philosophy. Meet the log-structured merge tree, or LSM tree for short. If the B tree is the meticulous organizer, this is the relentless appender. An LSM tree throws the whole idea of in-place updates right out the window. Instead, it treats the database like a journal, an append-only log that you can only write to the end of. When you update a record, you don't actually change the old one. You just write a new version of it at the end of the file. Same for deletes. You just add a little note called a tombstone that says, hey, this record is gone.
Now, I know what you're thinking. Wait a minute, doesn't that get super messy and really slow to read? And you'd be right if it wasn't for the secret sauce of LSM Trees, a background process called compaction. See, new writes go into small, sorted files. Then, behind the scenes, the system is constantly merging these small files into bigger, more organized files, cleaning up all the old versions and deleted records as it goes.
It's like having a little robot that's always tidying up your desk.
So why on earth would we go through all this trouble? Well, it comes down to one simple fact. Writing sequentially to the end of a file is the single fastest thing you can possibly do with a disk drive, period. This makes LSM Trees absolutely unbeatable for write-heavy workloads, where you need to ingest just a massive amount of data as quickly as possible. Think logging systems, analytics, or real-time event streams.
So there we have it, the Meticulous Organizer versus the Relentless Appender, the B tree versus the LSM tree. So which one is better? Well, the answer is neither of them. Like pretty much everything else in engineering, it's all about trade-offs. There is no magic bullet, no single best solution for every single problem.
Let's just put them side by side. B trees, they shine in read-heavy workloads. Their key move is that in-place update. But their main challenge is something called write amplification. Sometimes a tiny little change can force the database to rewrite a whole bunch of data blocks. Now, LSM trees, they're built for write-heavy workloads. Their whole game is appending and compacting. But their challenge is read amplification, because to find the latest version of something, you might have to check a few different files before you find it.
And this brings us to the language that engineers use to talk about these problems, the amplification factors. Read amplification is how much extra work you do on a read. Write amplification is all the extra writing the database does behind the scenes, like that compaction process. And finally, space amplification is the extra disk space you use up by temporarily storing multiple versions of the same data. Every single storage engine out there is in a constant balancing act between these three forces.
In fact, there's even a formal mental model for this called the RUM Conjecture. It's a really helpful way to think about it. It basically says that for any storage system, you cannot minimize all three overheads, read, update, and memory at the same time. It's impossible. If you make one better, you almost always have to make another one worse. It's this fundamental trilemma that you have to navigate every time you choose a database.
And that's the bottom line. The performance, the reliability, even the cost of running your application all comes down to these deep, fundamental trade-offs that were made inside its storage engine. So that brings me to my final question for you. Do you know which engine you're running on right now? And more importantly, are the trade-offs it makes